It's always great to get back here to A&M. One of the missed parts of my background is I was faculty here for about 3 years before I moved up to Idaho National Laboratory. So A&M is near and dear to my heart from my own background. I've got a son here now too. So look forward to opportunities to come and visit as much as I can, and very happy to be on the External Advisory Board. Looking forward to getting to know more of you and more of what the Energy Institute does, because I do believe we are at a significant crossroads in our energy systems. We as a nation and globally are looking to decarbonize. We are looking at how we design our energy systems differently, yet still maintain reliability, resilience, power availability, sustainability, all of these different aspects. And so today I want to talk to you a little bit about how nuclear energy can be a part of that. I don't want you to take away it all has to be nuclear. It all has to be one or the other. We need a mix for any of these solutions to be effective. So I'm going to first tell you a little bit about Idaho National Laboratory. Just give you a feel for where we are and what we do. We'll talk a little bit about the state of energy in the US, and then we'll dive into opportunities for nuclear energy and what we're doing at the laboratory to help accelerate that process. Somebody come sit up here in my seat. I don't think I need to sit down. All right. How many of you are familiar with the National Laboratory System? How many of you know that there's 17 national laboratories for the Department of Energy, located around the country? We each have some different areas of focus, and we also collaborate quite a bit. So Idaho National Laboratory is over here in Eastern Idaho, beautiful part of the country. Invite you all up to join us there at some point in time. We're only about an hour and a half from Yellowstone National Park, so really a great place to be, and a huge legacy for the laboratory there. So the DOE laboratories do span the spectrum from conducting basic science types of research up through applied science and technology. Some of those focus on single program areas, such as some of our accelerator laboratories, others being multi-purpose science labs, multi-purpose security labs, and then Idaho National Laboratory sits down here as one of our energy technology laboratories. So we're an applied energy lab. That doesn't mean we don't get over into this side of things, but our sweet spot is in the applied energy area, where Idaho National Laboratory is managed by the DOE Office of Nuclear Energy. So nuclear energy is our primary focus, but as you'll see, we do a lot more than that as well. And then our sister laboratories being the National Renewable Energy Laboratory for renewables and the National Energy Technology Laboratory for fossil energy and carbon management. We do focus our work around 5 main mission directorates, 3 of which do focus on that nuclear energy side of things. So our nuclear science and technology, where we do a lot of modeling, simulation, development of reactor physics codes, understanding new systems. Our advanced test reactor, very unique facility in the world that allows us to do a lot of fuels and materials testing. The materials and fuels complex, where we do a lot of development of those fuels and materials, but also post-radiation examination, overall characterization. The Energy and Environment Science and Technology Directorate, which is where I now sit. I've been in that directorate for about 2 years now. That touches all the non-nuclear parts of energy systems. So the grid systems, our renewables energy work, so geothermal, wind, solar, water. And we do a lot of collaboration with the Renewable Energy Lab. And then wrapping around all of that, of course, is security. Physical security and cybersecurity, which comes into play in all the work that we do. All right, so let's talk about the global energy challenge. We as a nation have said we are going to go to net zero electricity systems by, does anybody know the year? 2035. That's not very long from now, 11 years. But then we want to go net zero across all of our energy use sectors by 2050. That's a really big challenge. If we look at how we meet our energy demands right now, it's still 80% fossil fuels. So this is looking broadly at total energy consumption. So electricity, heating, industry, and transportation. If we look at this for just electricity, it looks a little bit better, but it's still almost 60% fossil fuels. So if we want to have clean energy systems, we have to think broadly. We have to think about how we do these things differently, how we grow this renewable sector, how we grow the nuclear sector, and how we use that to meet all of these energy demands. So that's what we'll talk about. I have to say, we've made a lot of progress and reduced some of our emissions overall. But I think the number was for 2022, that was at a global investment of over $1 trillion. So this costs a lot. We have a lot of work. We have to think in new ways. Okay, so the US Department of Energy has really put efforts behind this clean energy transition. They've now announced what are called Energy Earthshots. They've announced 8 of these, and we expect more to come. And they all focus on areas where that big push of effort and dollars is expected to accelerate breakthroughs of more abundant, affordable, reliable, clean energy solutions this decade, helping us to get to that 2035 goal of zero emission electricity and well along the way toward the 2050 goal. So when we start looking at all of these, I've got specifics on what each of these entail if you're interested. But 3 of them can be very directly influenced by inclusion of nuclear energy. Production of clean hydrogen at a very aggressive goal of $1 per kilogram of hydrogen. Industrial heat, replacing the heat that's primarily provided by fossil fuels right now and reducing industrial emissions by 85%. And then the clean fuels and products. So what comes next from those industries, the chemicals, the fertilizers, the steel, all of these different areas also looking to 85% reduction in GHG emissions. There's been a number of studies looking at how we get there from here. How do we get first to that clean grid? So looking across these studies, you can see a low case for nuclear, a high case for nuclear, and an infrastructure or renewable limitations study area. Each of them have some different parameters for what those are, the boundary conditions on each of those cases, which is why they're left fairly general here. And that infrastructure limited starts taking into account siting considerations, transmission considerations. In general, it will cost more and take more investment to connect more renewables into the grid than nuclear because of the distributed nature of the technology versus the highly dense energy source that nuclear energy provides. But bottom line, when we look overall, not just at one technology or another, all of these studies start pointing to the fact that the US needs an increase of 550 to 750 gigawatts of clean, firm power to reach net zero emissions just in the electricity sector. So what do I mean by that? So firm, meaning we can provide that electricity in all seasons. Flexible, meaning that we need flexible resources to match that variable supply that comes from wind and solar. And we need to go then beyond the grid to look at those non-electric energy demands, heat demands. Now that could be through electrification, which makes that number go up even higher. Or it could be through direct provision of heat from these energy sources such as nuclear, geothermal, concentrated solar that can provide us thermal energy. So when we look across all of these studies, this is a summary that was developed by Nuclear Innovation Alliance just last year. We need advanced nuclear energy to provide anywhere from 75 gigawatts to 425 gigawatts of that power to complement all these other sources that will come online as well. Nuclear energy brings with it a lot of economic benefits overall. So I don't have a slide on it in here, but would be happy to talk about how these energy sources can replace existing thermal energy supply that's coming from fossil fuels and natural gas. So one question we get asked is, well, what happens to those communities when a plant is retired? A coal plant is retired. Wind and solar could come in there and provide that electricity if it's a good region and favorable for that. But what it doesn't provide is equivalency of jobs. It doesn't provide some of the same energy density. But if we replace that with small modular nuclear reactors, we see a lot more direct job replacement, very high value jobs overall. We see huge impacts to the local economy, and we can take advantage of existing infrastructure, specifically the transmission infrastructure, but in some cases, maybe more of that plant as well. So there's huge regional benefits associated with replacing that coal plant with a small modular reactor. And in fact, about 80% of the existing coal plants in the US could host a small modular reactor. So what's the value proposition brought by multiple clean energy sources? Are any of you familiar with the DOE liftoff reports that came out last year? Few nods, not too many. So DOE has done a series of liftoff reports to say, what would it take for this technology to move to the commercial sector? So they did one on advanced nuclear that I think is very informative. And what I love about these reports is they're not 300 pages. They're maybe 20 or 30. They're very concise. They lay out the results in a fairly approachable way. So they looked at these energy options for their attributes. Are they clean? Are they firm? How much land do they require? What does it require with regard to transmission build out? Can we take advantage of what's there? Do we need to build a lot more transmission and distribution? Do they bring any local economic benefits, or do they see a decline based on these systems? Can they support additional applications? So getting into that industrial energy use, transportation, all of those other aspects where we need energy. And are they cost competitive? So as we look down across these technologies, you start seeing that many are hitting in some of the areas. Many have some gray areas that we need to leverage. Some of these require, like renewables, may require storage to be introduced with that to allow it to be more applicable across all of these different areas. Nuclear hits on all of these with the exception of that last column, cost. Nuclear is still very expensive. We haven't built much nuclear in the last few decades. But overall, what we can see is if we take a broad portfolio of renewables, flexible energy sources, and nuclear, we can get to cost-effective solutions for our carbon-free energy system. So let's dive a little bit into that cost question. But first, I forgot I put this in here first. How can we better utilize nuclear? So right now, nuclear energy is this red bar. I don't expect you to be able to see the numbers. This is a Sankey diagram. You can download these from Lawrence Livermore National Lab. All of that nuclear energy goes to electricity generation. But what does nuclear fission primarily produce? Heat. A lot of heat, a lot of high quality heat. So if we better leverage that, we can begin to see, this is totally conceptual, so don't start looking at width of lines and all of that. If we look at how we can use that more effectively, we can start seeing heat use, district heating, industrial heating. We can also provide flexible electricity to the grid. We can use that to support transportation through electricity or through hydrogen and hydrogen fuel cell vehicles. And we can begin to look at derivatives of that hydrogen, heat, and electricity to produce synthetic fuels for industry or transportation. We can look to many commercial applications and really begin to impact the overall emissions from all of these sectors. So what's the status of nuclear energy? Okay, so first, a few more facts about nuclear. We talked about it's clean, it takes very little land. So nuclear here is down at the bottom. For the same energy production, so this is normalized, this is the relative amount of land that would be required by the different energy sources. So if we're looking at constrained areas, maybe an island nation, we need to think about footprint. We need to think about how much space that will take up and how those resources will be utilized. We also need to look at how much those are operating. So nuclear energy dwarfs other energy sectors with regard to capacity factor. Again, don't take the message it all has to be this, because once we start dominating with what is traditionally operated as baseload, then this number will go down because we need to flex. So please recognize that we need all of these things, but we need to take advantage of the fact that fleet-wide across all of our plants in the US in 2020, we had a 92.5% capacity factor. And that accounts for downtime for standard operations, just standard maintenance and refueling. So if we start looking at that, combined with all of these other technologies, we can really start to understand where the investments go in our energy systems. And I put this in here because I know I'm always going to get the question. Is it safe? Is it clean? What are we doing with waste? So I just want to put it out there straight away. So these numbers come from operation of a very large number of plants around the world, looking at death rate from accidents and air pollution. So even including those nuclear accidents that probably all come to mind, we're sitting down here with wind and solar. As far as impact from a safety perspective, nuclear energy is highly regulated, highly safe, and advanced reactors bring in even more safety approaches in how they are designed. Greenhouse gas emissions, again, we're all right down here. In fact, nuclear has the lowest. And this takes into account life cycle emissions. So the transportation upstream, downstream, acquisition of materials and fuels for all of these technologies. And like I said, I just want to get it out here right now. What about the spent nuclear fuel? Well, it's really just used nuclear fuel. We could reprocess it and thus start closing the nuclear fuel cycle. We can store it. And in fact, since the 1950s, all of that used nuclear fuel from the commercial nuclear sector would fit on a football field. So you go put it on a tile field, it'd be less than 10 yards high. So there's not that much to deal with. We have technical solutions to that. And I don't think I need to share here how that relates to coal pollution and the waste associated with that. That is more than the lifetime of the nuclear plants is significantly less than what we see annually from coal. So we need to do something. Okay, enough of getting on that soapbox. What advanced reactor technologies are coming into our portfolio? So right now in the United States today, we have 93 large-scale reactors. So a large-scale reactor means it's about 300 to 1,000 megawatts, with most of ours operating at close to that 1 gigawatt of electricity. Many reactors are looking at power upgrade, gaining efficiencies in our current system so we can actually get more out of those. And because they're so large, in some cases, it will look like adding another generator to the grid. So we can make more and more progress in that way. But what's really exciting now is we're starting to see development and move toward commercialization of small modular reactors at that 20 to 300 megawatts of electricity and micro reactors on the megawatt scale. These large scale reactors take about 1,500 acres. That was the equivalent when I showed you those dots just a minute ago. When we start looking at small modular reactors, we can look at 50 acres, and a micro reactor could be less than an acre, meaning we could take those and embed them into a chemical plant facility, embed those into small communities, a military base, mining operation, really starting to bring the right size system to the right applications. Meaning now that these would be on par with those renewables that might also be brought into a microgrid situation, into those applications, and not be such a large chunk of the power in that area, but now giving us an opportunity to transition energy and power back and forth much more readily because they are on par with one another. I promise I'm going to get there. We go cost. I thought it was coming up before that. So what about the cost? In 2018, MIT conducted a future of nuclear study. This is one in a series of different studies that MIT has conducted in the past. And it really began to address what is going to be this role of nuclear energy. How does the inclusion of nuclear energy or the lack of nuclear energy really begin to impact the grid, the cost of achieving net zero? Overall, you see, and I'll show a chart here in a second, that without the contribution of renewables and nuclear, costs go up dramatically for that decarbonized grid. And when we start looking at least cost portfolios, the cost of those goes down significantly when we include nuclear, but then as the cost of nuclear itself drops, we see more and more being built. So a more balanced mix overall. So why isn't it thriving? It's cost, it's public concern, and it's energy policy. These last two we're beginning to address significantly, and I'll show that. So just a snapshot of the output from some of that study, where we can look at on these charts on the left, let me make sure. Yep, charts on the left, more constrained emissions. So going from 500 grams CO2 per kilowatt hour down to 1, so near zero, in 2 different regions. So in the United States and in a region in China. Because we do have significant differences in the cost to build these projects in different countries. The numbers that went into this particular study was $5,500 per kilowatt electric in the US, and a low case of $4,100 per kilowatt electric. China has done a much better job and built these much more efficiently at less than $3,000 per kilowatt. So this was $2,800 for the high case and $2,100 for the low case. That liftoff report I mentioned, I think, used $6,000 for the cost of new nuclear. What I want to point out is in these charts, you see no nuclear is the orange bar, low cost nuclear being the yellow, and then a nominal cost in the blue. Throughout this, when we don't include that firm, clean power in the mix, the cost goes up significantly because we have to overbuild capacity to account for that low capacity factor, and we have to overbuild storage to ensure that we have reliable energy supply. On the right, you can begin to see how much nuclear energy is installed based on cost of nuclear and the overall constraint on carbon emissions. So it helps us get us to that end goal, but it helps us get there with less investment overall, even if nuclear is really expensive relative to some other energy sources. Yes?
Because one thing that is interesting to notice is that you compare the New England region with the Tianjin, Beijing region in China, the cost difference between the orange bar and the blue bar are 5 times different.
Yeah.
Which I don't understand, like, what is the reason for that? In both cases, if you have no nuclear, why is one region cost 5 times more to achieve the same goal of carbon reduction? Was it because of the base number being different?
Yeah, primarily, and I'd have to go dig into the math and look back into that. But because those base numbers are so different, it makes a huge difference in the end in how much is built and the overall system cost. Because here you'll also note that there's a different number being built here versus here. And so there's additional system cost associated with the non-nuclear kits there. So just a quick summary there. How do we reduce cost? We need to introduce proven management systems. One of the challenges also is some of these plants, so the plant Vogel in Georgia that just recently got Unit 3 started, is about to finish out and get Unit 4 started. One of the challenges there is, number one, we haven't done a large mega scale engineering project in this country in a very long time. So project management had some growing pains to get back into that. They also entered that project with about 50% design complete, meaning a lot of field changes and a lot of delays. So if we can bring in project management approaches and say, no, we don't break ground until we're 85% done on that design, so that we know what it's going to look like from a regulatory perspective, and changes become very minor and less costly. We also need to shift away from field construction to factory construction, and that's where these smaller systems really begin to give us a benefit overall. Public concerns dramatically improving. I'll show you a chart here in a second. And also we see advanced reactors that incorporate inherent and passive safety approaches. And then policy, we need to make sure all of these technologies have a level playing field. So this has been really significant, not just in the US, but also in other countries that are starting to use different language around clean energy, not renewable energy credits and portfolio standards, but clean energy credits and portfolio standards. So I encourage you always to think about what's the end goal. The end goal is no emissions, not let's promote one technology. So we're starting to see the language in the policy change in many different countries around the world. So digging in a little bit more on nuclear economics, any new system is going to cost us more. We're learning, we haven't built it before, it's going to cost us quite a bit more. You'll note that there is no number on this y-axis, that's intentional. This is intended to show where can we have cost savings, whether we're starting with numbers like in the US that I showed, or China that have been able to bring some of those numbers down significantly. So let's say our first of a kind plant, our first of a kind reactor is way up here. As we mature that design, we implement effective project management. We introduce regulation, stability, and predictability of the regulatory approach. And we start building more units that look the same. We can bring down the cost of reactor number 2, number 3, almost not by half, 40%, by about 40%. These are learning curves that are well documented, and we can begin to bring that down. We've seen the same sort of thing happen in the renewable community that have brought those costs down. But then if we repeatably build that, how much would it cost to build the next unit, the subsequent units? We can begin to see more and more design optimization, process innovation, more regulatory interactions, harmonization of codes and standards and licensing, such that we can get down to less than half the cost of that first unit. We need to get here. This is one area where the US is not doing well. We look around the plants in operation today for nuclear, they're all different. Everyone has something unique. In France, at one point, they were as much as 90% nuclear. They're now at about 75%, and that was done very cost effectively and very rapidly because they took the same design and put it in different places. We don't do that well because of free market approaches in the US, but as we go into small modular reactors and factory manufacturing of smaller systems, we can get here and address this cost question. And I said I was going to show you a chart on favorability. So this is tracking from 1983 to 2023, favorability toward nuclear versus opposition. We're doing a better job. We can get past this social aspect and show these overall economic benefits and social benefits of bringing in these advanced technologies. Okay, so what reactor designs are out there? I talked a bit about microreactors, small modular reactors, and full scale. We're also introducing new concepts around these reactor designs. Universally, these adopt inherent or passive safety, meaning the laws of physics. It's not depending on reactor operator A and B, but instead on laws of physics that are immutable. They adopt deployment flexibility approaches so we can do this more repeatably at different locations. So designed from the start to support versatile applications, very long fuel cycles. So instead of changing out the fuel every 18 to 24 months, we might do that every 5 years, 10 years, or the lifetime of the core. Thus reducing waste and introducing advanced manufacturing and factory manufacturing to get to that end goal. So they do adopt, in some cases, different fuel types, different coolant types like molten salts, liquid metals, and gas-cooled systems, helium cooling. This allows us to operate at higher temperatures and thus support more of those industrial applications that need that high quality heat to get rid of that fossil energy source that they're currently using. So I'm going to skip that one, talk to that. Okay, 10 years ago, here was our advanced reactor timeline. Not very exciting. We had one small modular reactor that was being planned. That was a NuScale light water cooled system. Unfortunately, that project was just canceled a couple of months ago, but that was all it looked at. If we look today, that timeline looks very, very different. We are moving forward with this recognition that we need nuclear technology to meet these decarbonization goals. We need to demonstrate, and we need to do it quickly. So a few things on this chart. Number one, all of these projects on here have involvement of Idaho National Lab in some way. This is not comprehensive of everything going on in the US and certainly not of the global space. So INL is involved in some way. We've made an assessment here to say, are these real systems? Are they moving toward demonstration in a way that we believe is accurate? Meaning company XYZ that has a wonderful reactor design on their computer, but has never built any hardware, isn't going to show up on here. These are designs that we see marching toward demonstration and deployment, and that we see have a very strong approach for their regulatory approvals. So they're working with the NRC, they've got a plan on how they're going to get their systems licensed. So these systems, some of these are test beds and test reactors on the bottom. On the top, these are actual demonstrations. So quick note on these numbers. So 53, 54, 51. INL used to be the National Reactor Testing Station. We have tested and operated 52 reactors to date. So Marvel is a very small microreactor, 100 kilowatts thermal, that we will be building in 2025. That will be number 53. That'll be right alongside Project Pele, which is a Department of Defense developed microreactor that will be demonstrated in 2025. Moving forward with molten salt cooled systems. So this is a liquid metal system. This is a gas cooled system, molten salt cooled system, marching all the way through to where we see significant development of these systems to move the needle on commercialization. Point out a couple of those down here because they relate very much to the region. One is the Natura Resources that is working with Abilene Christian and several national laboratories, as well as several universities, including Texas A&M, to build a test reactor facility at Abilene Christian. And X Energy, which is working with Dow Chemical to build a plant, their first plant at the Seadrift facility. So integrating directly with a chemical process for their first demonstration. So really starting to move beyond just that electricity focus overall. And I'll also point out this natrium reactor that's TerraPower and GE. It's a sodium cooled system that will go into a retiring coal plant in Wyoming. So demonstrating that pathway as well. So keep your eyes on the ball here. There's a lot happening. And this is all around the country. So here what you see is in red. Okay, so I need to remove NuScale now since that one's not going forward. But these are demonstration reactors. These are commercial reactors, initial demonstrations of some of the test needs. In green, you see the associated fuel fabrication facilities. So we need to make the fuel that goes into these reactors. And we see our first opportunity for commercial scale production of high assay, low enriched uranium, meaning going to higher percentages of uranium-235 than what we use in our reactors today. We're starting to put that supply chain together. We're getting the resources in place to make this real. And those first 3 reactors that will be built on the INL site in over 40 years are just illustrated here. So Marvel, Department of Defense, Project Pele, and the molten chloride system. Okay, so energy systems integration. This, I think, is going to be the wave of the future and how we implement these systems. So we look at many of our plants today, they're singularly focused. We have a nuclear plant providing electricity to the grid. We have a renewable plant providing electricity to the grid, and we have grid operators managing that. As we begin to truly shift that energy paradigm, what we see is that we begin working with energy currencies such as heat, electricity, hydrogen, and carbon, and closing that carbon cycle to get to some of these other applications, providing flexible electricity alongside these other generation sources, in some cases intimately integrated in an energy park, district heating, water purification, hydrogen production and utilization for transportation, chemicals manufacturing, ammonia manufacturing. You'll see a lot of discussion around hydrogen, and that is because it is kind of an entry energy carrier that can get into so many of these different hexagons along the bottom. And right now, hydrogen is made primarily from steam methane reforming, meaning we take natural gas, combust it to get a lot of heat to break down other methane, and we have a lot of emissions associated with it. That's 95% of the hydrogen in the US today. So if we can do that from splitting water, using these high quality, clean energy sources, then we can decarbonize that whole value chain and really begin to make an impact. So overall, this might look something like bringing in your nuclear technology at whatever scale, supporting grid demand, but then also using heat and electricity for an industrial plant or a chemical plant, hydrogen production that can then go into all of these applications on the right. And we're starting to utilize those carbon sources. Now, maybe that's point capture from something like an ethanol plant, or maybe we make significant advances in direct air capture. There's a lot of costs that need to come down on that as well. But that then becomes a feedstock to things like transportation fuels, there it is, synthetic aviation fuel, synthetic diesel, which still will have emissions associated with them when they are combusted. But now we've captured that CO2 and we've started closing that cycle. One of the questions we have to address is, what's the market for that clean hydrogen? So the Department of Energy, in its love for roadmaps, started looking at that and saying, how much will this grow? What do we really need to get behind this? Can renewables do it all and just produce via low temperature electrolysis? The prediction on the growth in the hydrogen market just in the US is fivefold from 2030 to 2050. And that means using this clean hydrogen in existing industries like ammonia to make fertilizers, or ammonia just as a chemical in refineries, so cleaning up the refining process, but then also these sustainable aviation fuels, steel manufacturing, and then potential exports. So we started looking at how we can use these nuclear plants to produce that hydrogen. So INL focuses on high temperature steam electrolysis, meaning using some of that thermal energy as well as electricity from the nuclear plant, which allows us to produce hydrogen from steam at 20 to 30% more efficiency than low temperature electricity only electrolysis. And our colleagues at the Renewable Energy Lab focus on low temperature electrolysis. But when we looked at integration of an existing nuclear plant that has times of flexible operation, needing to cycle from electricity production to either dialing back their power output or sending it to another application, we looked at coupling that thermally with a high temperature electrolysis system to serve the regional hydrogen market. And we include hydrogen storage to make sure that we can always serve that market, not just when we have the energy available. Overall, this study showed that one particular plant that we were looking at had a $1.2 billion increase over the remaining lifetime of that plant. So this was sufficient to convince the plant owner and operator to take the next step and move toward follow-on work and demonstration of that in hardware at their operating nuclear plant. And this chart's just here to show you the cycling based on grid price of when we produce hydrogen and when we dispatch from storage. So back in March, Constellation started the first hydrogen production at an existing nuclear plant. 5 years ago, I had colleagues at the lab say, nobody is ever going to do that in an existing plant. It's too difficult. It complicates operations. But if you have sufficient motivation to decarbonize, sufficient motivation to keep your plant viable from an economic perspective, the impossible sometimes happens, and we are operating right now. And that will be followed by 2 more demonstration projects at existing plants this year and follow-on hydrogen hubs that are around the country, 2 of which explicitly use nuclear energy. So what about then the next steps? What are we going to do with that hydrogen? So we've done some studies here, and this just shows some of the preliminary results, the rest are being reviewed now, of how we make those synthetic fuels. So I mentioned using a reactor to produce that hydrogen. Here we're capturing CO2 from a neighboring plant, combining that with that hydrogen using a Fischer-Tropsch process to produce gasoline blend, diesel, jet fuel. And we can begin to evaluate how viable that is. And we're looking at other pathways as well. So in this report, this was the first cut report, and there's a follow-on that I don't have available here, to look at if you did that, is that resulting fuel going to be cost competitive? So here you can see a difference in the scale of the plant and how that impacts the overall price of the selling price of the fuel. The cost of hydrogen is still highly dependent on the cost of electricity, because about 80%, even in a high temperature system, is coming from electricity. So you can see for low cost hydrogen at $2 per kilogram, high cost hydrogen at $4.50, or that hydrogen earthshot goal of $1, where we land relative to the 15-year high for diesel and the 15-year average. So when we start looking at those average prices, as we bring down the cost of hydrogen, we're competitive with the fuel that we buy today. But now we're much cleaner, much lower emissions overall. Now I wanted to show just a magnitude example. So we talk a lot about electricity, but what about when we start looking at these heat applications? So decarbonizing steel. I borrowed this next set of slides here from a colleague in Europe, Staffan Kvist, and he's working with a gentleman, David Victor. He's at a university here in the US, I can't recall which one. Looking at what we're really talking about when we talk about replacing emitting sources. So iron and steel contribute to 8.5% of the global CO2, more than air, ship, rail, cement combined. So it's huge. How do we really decarbonize this? Right now we have 2,000 kilograms of CO2 emitted per ton. And it goes through these steps where you've got oil and coking coal and electricity to result in those. But if we go through a different process called direct reduction of iron, we introduce hydrogen from these clean hydrogen processes, we eliminate those emissions that I showed across the top. So this is a great pathway. We can get rid of all those emissions, but how much energy does this really take? For primary steel, it takes 3.6 megawatt hours per ton. Secondary steel, meaning from scrap, 0.6 megawatt hours per ton. That energy requirement for producing 1 ton of green steel is equivalent to the annual global per capita energy consumption in 2022. So remember those numbers from that first chart, the 550 to 750 gigawatts of additional clean firm power, and just add these numbers to the top of it, because that was only for electricity. So if we wanted fully green steel, we need 680 of those gigawatt scale reactors to produce it from ore. And steel production is increasing and expected to continue. So this is the magnitude of the problem and why we need these highly dense energy sources to help support it. All right, what are we doing to demonstrate this? I know I'm running out of time. I always talk a lot longer than I expect to, so apologies. So we talked about these energy currencies: heat, electricity, hydrogen, and carbon. So how are we demonstrating how we can actually integrate these things? I showed an example of nuclear going to hydrogen, but what about when we put them all together? Number one, we're doing a lot of development in hydrogen technology, ranging from materials preparation through cell and stack manufacturing, and then getting into these systems, really understanding how systems perform overall. Right now in our laboratory, we've been testing a 100 kilowatt system producing about 60 kilograms of hydrogen per day. Overall, that's not that much. We do individual stack testing in a much smaller system. And we're about to install a system that is 250 kilowatts as soon as the company ships it to us. So at this scale, it's a lot of laboratory research and development. As we get to the large scale, we're working with industry to demonstrate and test their systems. So we look at stack testing, make sure we understand the performance of individual components, up through small scale systems. This is just showing where the heat comes in. I'm going to skip that and send this out. Commercial scale systems, where we've demonstrated more than 5,000 hours of operation, sent that data, sent that system back to the company so they can make some tweaks and then better understand performance, how they can improve that even further. But even after 5,000 hours, we didn't see any degradation in the system. So this is all non-nuclear testing using a steam generator. And then when we install our larger scale systems, we need to do something with the hydrogen. Right now, we just vent it, which is painful. We're not using this great, valuable energy currency. So now that we're going to larger scale systems, we'll be compressing that and using it for fuel cell vehicle charging or fueling. The INL site is enormous. We're 890 square miles. We have about 2,000 staff that work out in the site facilities, about 6,000 staff overall, and we bus them out to the site every day. Meaning we have about 80 buses that take our staff to the site every day. And they're usually using biodiesel. We have one electric coach, and we're working to acquire our first hydrogen coach this year. I mentioned that we have several of these demonstration projects looking at how we better utilize our nuclear energy systems we have today. So this first being the one that I showed started operation in March. Energy Harbor Davis-Besse plant in Ohio beginning this year, and Xcel Energy Prairie Island also beginning production this year. And that will be followed by integration of these systems with more system design. So we're doing a study with Westinghouse looking at how do we integrate these existing facilities with hydrogen production, whether they be pressurized water reactors or boiling water reactors. And then taking that next step in chemical synthesis to understand, well, what if we perform co-electrolysis? So rather than going through electrolysis of steam and producing hydrogen, and then getting that CO2 producing syngas, and then down to those synthetic fuels, can this be done at one step? So co-electrolysis of CO2 and steam to directly go to those synthetic fuels. And we'll be demonstrating that in one of the facilities at INL later this year. We do a lot of this work in a non-nuclear test lab that allows us to emulate nuclear energy using electric heating. So you see a microreactor test bed here and thermal distribution and thermal storage systems. These connect to the hydrogen systems that sit on the other side of this wall. But we have opportunity then to run those within real-time grid simulation. So microgrid environment, we can understand how it interacts with renewables also in that grid. We have some renewable facilities that sit outside. And we can understand how that interacts with different energy users as well, such as electric vehicle charging, that can be highly dynamic in load. And this, I think, is really exciting. We're taking it to the next step. So when we do this in-town demonstration, these are at the kilowatt level. Even the demonstrations at the nuclear plants right now are fairly small scale. We need to take it to the megawatt level. Anyone here who does experimental work knows that if you work on the benchtop at very small scale and think you can just jump to hundreds of megawatt scale systems in one step, you'd laugh at me if I said we were doing that, because it's just, you don't know the engineering challenges. So I mentioned that INL is a very large site, and we have space out in the desert that allows us to take it to that next step of multi-megawatt systems to prove the integration of these technologies and how those can be a significant contributor to our energy future. So this allows us, this is conceptual. Right now it's pretty blank, few buildings out there, but we'll be bringing in technologies to demonstrate high temperature testing and hydrogen production that pad is already poured and we're ready to bring in hydrogen later this year. At the 5 to 10 megawatt scale, we're still looking at which company will bring that in. Biomass and waste carbon processing, thermal energy and carbon management systems, integration of all these technologies, and of course, ultimately bringing in microreactors to the site to integrate in this facility as well, and demonstrating what this might look like for a community. Opening that up to electric vehicle charging, hydrogen refueling, as well as using synthetic fuels. All in all, this proving ground supports 6 of those 8 Earth shots I showed you at the beginning of this. So really helping to take this to the next level and fill those gaps on development in that megawatt scale for hydrogen, industrial decarbonization and electrochemistry, biomass and waste carbon, transportation and energy storage. All of that coming together in this facility, and we'll be working significantly with industry to make that happen. And all of that will help us to become a net zero laboratory, which we've committed to doing by 2031. So I'm going to stop there and leave this vision slide up. I know we've got 5 minutes, so
Okay.
I apologize for talking too long.